A very good afternoon to one and all. We are gathered here at the intersection of curiosity and innovation. Today, we are truly privileged to host a scholar whose work bridges the gap between fundamental physics and the future of technology. Please join us in welcoming our guest speaker, respected Professor S.B. Kondawar sir, who will be enlightening us on the fascinating frontier of frozen light, a unique state of matter and its importance for quantum computing. Tradition is the foundation of innovation. I request all the dignitaries on the dais to kindly proceed for the floral tribute to the portrait of Dr. Panjabrao Deshmukh and Rashtrasan Tukroji Maharaj. I now invite Honorable Dr. O.S. Deshmukh sir to formally welcome our guest of honor, Professor S.B. Kondawar sir, with a floral bouquet as a token of our immense respect. I request respected Professor S.W. Anwane sir to welcome Honorable Dr. O.S. Deshmukh sir. I request respected B.T. Kumbhare sir to welcome respected Professor S.W. Anwane sir. And I now requested respected Dr. G.L. Jadhav sir to welcome B.T. Kumbhare sir. Before we begin the technical session, I invite our head of department, respected Professor S.W. Anwane sir, to the podium to share a few words.
Thank you very much. As we all know that we are assembled here for the guest lecture by Professor Kondawar, I pay my tribute to Dr. Panjabrao Deshmukh. Dr. Kondawar sir was faculty member in this department. In 2003, we joined this department. Then later on, he shifted to Nagpur University, physics department, and presently he is retired as Pro-Vice Chancellor of RTM Nagpur University. As Dr. Kondawar sir is well aware with our tradition that we are having physics society and students are office bearers, and they are arranging this activity under the guidance of teachers. Professor B.T. Kumbhare is in charge of physics society, and we have coordinated this activity for students. So without wasting time, I would conclude my say and request to continue the proceedings.
Thank you, Professor Anwane sir, for those insightful reflections. Now I call upon Mr. Shubham Chalke for the introduction of Professor Subhash Kondawar sir.
Good afternoon to one and all present here, distinguished guest, faculty members, and students. It is a profound honor to introduce our guest speaker for today's lecture on the fascinating subject of frozen light. We are joined by a scholar whose career embodies a perfect blend of academic leadership, pioneering research, and dedicated teaching. Honorable Professor Subhash Kondawar sir is the former Pro-Vice Chancellor of Rashtrasanta Tukdoji Maharaj, Nagpur University. His illustrious career at the university includes serving as a senior professor in the Department of Physics, chairman of the Board of Studies in Physics, and head of the Department of Statistics. He earned his MSc and PhD in Physics from the Government Institute of Science, Nagpur. With an impressive 37 years of teaching and research experience, Professor Kondawar has shaped the minds of generations of scientists. His contribution to the scientific community are vast. He has authored over 150 scientific articles in international journals of high repute. He has written 2 books and 21 book chapters, primarily focusing on polymer-based nanofibers and nanocomposites. He has successfully guided 29 PhD students, fostering the next generation of researchers. He has delivered numerous keynote addresses and chaired sessions at international conferences in countries such as the USA, UK, Japan, South Korea, Sweden, and China, among many others. Back home, his leadership in securing research funding has been transformative. He has coordinated the DST FIST program, managing a grant of 1.47 crores. He currently serves as the chairman of the DST Fund PERS project, a major initiative with a grant of 11.133 crores. Notably, his PERS team was recently felicitated by the Union Cabinet Minister, Dr. Jitendra Singh, at Vigyan Bhavan on National Science Day in February 2025. His dedication has earned him several prestigious accolades, including the International Advanced Materials Scientist Award 2013 in Turkey, the Best Researcher Award 2022 from RTM Nagpur University, the Vidarbha Bhushan Award 2022. Most recently, he was named a Fellow of the Maharashtra Academy of Sciences in the December 2024. Today, we are privileged to hear his insights on frozen light, a unique state of matter, and its importance for quantum computing. In a world where speed is everything, today we learn why stopping light might be the key to the ultimate computer. Thank you. Without further ado, I request Professor S.B. Kondawar sir to take the podium and lead us through the mysteries of frozen light. Thank you.
One and all present over here. It was a very nice introduction given by Shubham, and I am very happy to be here because I have started my teaching career from this institute when I joined in 2003 and later in 2009. As Dr. Anwane said, I joined Department of Physics, Nagpur University as associate professor, then senior professor, then various opportunities I could avail in the university. And last year in the month of October, I have been superannuated from the post, and at the last I work as a Pro-Vice Chancellor. Within that duration of the 7 months of the Pro-Vice Chancellor, I thought that I can do something new for the researchers, and I am happy to announce specifically in my resume for submission of the PhD thesis, there would not be necessary of hard copy for submission. So it was entirely soft copy to be submitted on the portal of the Nagpur University, and it has been started from this year. So I was the person who introduced this type of this submission of the PhD thesis for the researchers. Let it be. So I think before 2-3 years ago, I started this type of Bose Einstein condensation as the course of physics for MSc. This particularly statistical physics for the PG, I have designed a particular syllabus when I was the chairman of the Board of Studies in university. And this is a part of that particular course, and there are the students, hopefully for the first year in second semester, you have this statistical physics as one of the subject. Looking to that background, what you are going to study and what would be the new coming up after understanding this statistical physics, through which the new state of matter, whether it will be coming or not, that can be the particular point of today's and future research. Okay, and therefore I have selected a particular topic that would be very fascinating and interesting, specifically for the PG students, those who have interest in this particular subject. Though this particular subject, I have no any research related with that, but it is the topic of my interest. My topic of research is specifically related with nanoscience and nanotechnology. So I have prepared so much one-dimensional nanomaterials for different point of application. Here again, little bit nanotechnology come across while understanding this particular future of a particular material that we consider as a quantum material, and therefore a new computing process to be developed, known to be today's quantum computing, which is of course in developing state. And what is the importance of that particular material that we consider as a frozen light? What does it mean? So when you look to this particular title, frozen light, so there are three aspects. One is the frozen light, second one is the unusualness or exotic nature or a unique state of matter. What is that? And how it is important for quantum computing. So when we talk about the quantum computing, first of all, how does it differ from classical computing? Today we have a particular computer, whether it is a quantum computer or a classical computer. Of course, it's a classical computer, and everybody knows classical computer means today we are using the computing process in our computer is based on binary information, binary digits, 0, 1. Quantum computing is different. So it is based on the principle of quantum mechanics. The one thing is superposition, second one is the quantum entanglement. Superposition is the simultaneous occurrence of the two states like 0 and 1. So for better understanding, let me tell you a simple example. I hope you have answer of that particular simple example as a question. For going towards classical to quantum computing process, of course it is depending on the statistical probability, no doubt. If I toss a coin, what is the probability of getting head? What is the probability? Probability of getting head? 1/2. So what type of coin I mean? Have you thought about what type of coin I mean? Have you seen the movie Sholay? Amitabh Bachchan had one coin. It had only one head on both the side. What is the probability of getting head in that coin? 100% probability of getting head and 0% probability of getting tail, because there is no side of tail in that coin, right? So you have to concentrate on that particular point also. Now the coin means in our Indian rupee currency coin, having one is head and second one is tail. For that case, what is the probability of getting head and what is the probability of getting tail? Your answer probably 1/2. It is of course written in the book, and we can generally calculate probability. But for example, you just think that if I toss a coin and the coin is stand like this, neither head nor tail, then how we consider it? The probability is 1/2, right? Similarly, you know the example of Schrodinger cat in quantum mechanics. If the cat is blocked in a box, box contains a cup of poison, and the block and your cat is closed. Now you have to imagine what would be the status of the cat, whether it will be alive or dead. Quantum mechanically, it is alive, or it is dead, or it is alive and dead, right? Similarly, neither head nor tail for the coin So these are the three states coming out, which means that the simultaneous process that is known to be between the two proper states as a superposition. So in case of classical computer, 0, 1 binary bits giving the information for computing process. That is, we consider as digital electronics for the classical computer. Now quantum computer today's, which are existing beyond our supercomputer even, based on the principle by using the qubits, not the binary digits. Qubits, quantum bits. And therefore the name is given for such computing is quantum computing. Quantum bits. What are the quantum bits then? 0, 1, 0 and 1. Right? That is the superposition. So many states can coming up between 0 and 1. Which means that such kind of the idea keeping in mind, and therefore there is the process of developing such kind of the quantum computing. Now what is the need of quantum computing? With the help of quantum computing, we are able to solve so much complex problems which are not deliberately to be solved by even supercomputer. That is not the question for our computer that we are generally using. So first one, classical computer, then it's supercomputer, then quantum computer, then I am talking about the future of the quantum computing. That is the interesting one. Because today we are in the age of developing of the computer, that is quantum computer, then what is next? Today that computer, quantum computer is not completely developed, but scientists are thinking what would be the next after that? What are the problems of today's computer, quantum computer? How can it be solved? So I am talking about the frozen light, a unique state of matter. So you can clearly see there are the 5 states of matter. Everybody knows: solid, liquid, gas, plasma, and the 5th state is Bose-Einstein condensate. Right? These are the 5 states. Now frozen light, will it be the new state of matter? The question comes. Is it related with this same BEC, Bose-Einstein condensate, or not? So that we can have the question like that: 6th state of matter, it is related with the Fermi condensate. So our aim is to understand that Fermi condensate, will it be the 6th state? You just have a Google, you can see that it is the 6th state of matter, but it is not. There are only 5 states of matter. 6th state of matter, today it is not existing. Though such kind of Fermi condensate is possible, but it is not a new state, and it is similar to that of the Bose-Einstein condensate that our aim is to find out. So 5th state of matter, the Bose contribution that we will see, and how it will be applicable for the quantum computing, that we will see in this lecture. So Bose-Einstein condensate, then Fermi condensate, what is the difference? I am talking about the frozen light, a unique state of matter, whether it is a BEC or FC. Right? So those are the questions, and how it can be taken out. Of course, this is very simple. Everybody knows their interconversion of the existing 4 state of matter. The 5th state of matter that we are talking about as a Bose-Einstein condensate. And it is the main contribution given by our Indian philosopher Satyendranath Bose, who has given a lot. So who is the founder of the 5th state of matter that we consider, whose name is associated with Einstein? Later on, that the journey we will see during this particular understanding. So when I talk about the meaning of the frozen light, so what questions comes in your mind? How it is possible the light can be freezed, right? So we have the freezing of a water. Just keep a glass of water inside the refrigerator, whose temperature is less than 0 degree Celsius, right? Now the question comes that how the light can be freezed. So this freezing is not that particular case. Means light is not freeze, whether the meaning frozen light means the light is trapped. Okay, light is trapped, but the word is given to have a fascinating understanding: freezing light. How the light can be trapped again? So if the light is trapped, what are the possibilities to trap the light? So initially, the name is given freezing light, means particular Italian scientist who tried with his research team, the light has been frozen. Later on, instead of using the temperature near to 0 degree Kelvin, not 0 degree Celsius, 0 degree Kelvin, so it was possible. But today, that is a new generation of quantum computer, no need of ultra cold temperature of 0 degree Kelvin. The light can be trapped. That we consider as a photon of the light can be condensate. Now condensation process is not only depending on temperature, it is also depending on the density. So these are the two factors. Lower the temperature and higher the density, the process of condensation can occur. And therefore, the scientist could show not necessarily the requirement of ultra cold for freezing the light, whereas the light can be trapped, and the name is same as the light is frozen, so as to get a new state of matter which is very unique, exotic, unusual. Why it is called unusual? That we will see that it has dual property. One is considering as super solid and second one is super fluid. So super solid and super fluid, these are the two properties in a same material whenever the light gets trapped. So that is very interesting, and how that kind of the quantum material useful for quantum computing. So before going to the freezing of light by using a certain semiconducting material, let us have the basics of the statistical approach. Now, this example tells us about the quantum statistics, because both Einstein statistics, both Einstein condensate and Fermi condensate, which are the types of quantum statistics, and therefore we have to need to understand at the beginning what does it mean. Then it will be very easy to understand the condensation process. If I have two gifts, one is book and one is pen, for example, how can I give the name? Because I am talking about the classical idea. Classically, I have two distinguished gift, I mean, identified gift, one pen and one book. So classically, that is known as Maxwell-Boltzmann. Statistical approach is very sufficient to understand how many number of ways I have to distribute the two gifts to the three best identified students. If the students are X, Y, Z, the first table, okay, X, Y, Z, these are the three students. And the two gifts, here in the first picture is pen and book, P and B. We can identify these two, okay. How can we understand this example? Three quantum states X, Y, Z if we apply for that B and FD. So quantum states would be the same. So these are the three states. How do we able to fill these three states using the two particles, right? Two particles which are distinguished according to MB, but which are totally indistinguished. We cannot identify according to quantum. In case of B and FD also. How many ways? 9. It's very simple. So I can offer both the gifts to one student, first one, X. Second possibility is I can offer both the gifts to the second, Y. Similarly, I can offer both the gifts to the third. I can offer one P to X, B to Y, Z is empty, right? And accordingly, it is very simple possibility we can distribute. My question is that, what would be the nature of the gifts according to MB, B and FD? So MB is very clear. Any two examples you can select which are distinguished. कोई भी आप दो ले सकते हो. It is very simple. Now, when I talk about the B, quantum statistics and FD, since the particles are indistinguished, means book and pen, we cannot take. Both the pens identified not. We are not able to distinguish. We are not able to find the difference between the two such particles, two such things, such a two things, such a two gifts. How can I offer? According to B, according to FD, right? So here indicate that Question comes in your mind, if those are new for understanding, that X has 2, then Y has 2, Z has 2, again the same thing like this. What are replacing? PB, BP, PB, like these. They are completely replaced here in this case. So here in this case, PP, PP, PP means if you have the two gifts which are same, identical, PP, PP means pen, pen, right? You are able to give the question that how it is possible. One condition is that I can offer 2 to the one student. Means these B statistics do not follow Pauli's exclusive principle. चाहे वो 2 गिफ्ट रहे, 10 गिफ्ट रहे, मैं एक स्टूडेंट को दे सकता हूँ, right? Nature of the gift is indistinguishable and do not follow the Pauli's exclusive principle. Therefore, I can offer all gifts to one student like that. But fermions, Fermi-Dirac statistics, follows specifically Pauli's exclusive principle. No two particles can have the 4 quantum numbers. Same. Accordingly, no two particles would be in one quantum state. And therefore, I cannot offer 2 gifts to the one student. तो वो कट गया, double वाले. Leaving only the 3 states, 3 possibilities, 3 ways with which I can offer 2 gifts to the 3 students. What would be the nature O? कौन सा example हो सकता है? To understand clearly about the FD statistics, what would be the nature? ऐसा कौन सा example हो सकता है एग्जाम से फिट बैठेगा Pauli's exclusive principle के हिसाब से, अंडरस्टैंड होने के हिसाब से? Anybody? Let us move further so that you have to think over it. I will come again later. So you go through this particular case to have a better understanding. Quantum statistical mechanics for B and FD. Find the differences between the two, then you can think over what type of nature of the gift I am talking about. Particles are indistinguished, particles are indistinguished. Quantum में है दोनों. No restriction of the occupation of energy level. Energy level means quantum states. These are the 3 students for better understanding. No restriction. इसलिए 2 मैं एक को दे सकता था. Restriction on occupancy of energy level. I cannot offer both the gifts to one student. There is a restriction, right? Particles have integer spin. 0 or even integral multiple of h cross by 2. Spin means the spin angular momentum, I mean. So its spin is like n h cross by 2. N is even number, there n is odd number. That is the difference between these two according to the spin of the particles. Wave function is symmetric, wave function is antisymmetric. These are the differences you can find. So I can interchange the particles, there is no change in the sign even. When I interchange the particle, there is a change in the sign of the wave function. But wave function must exist in both the case. Occupation number. Number can be any 0, 1, 2, 3, 4 and infinite number. This is very interesting for understanding condensation phenomena. Because when I talk about the Bose-Einstein statistics, specifically the particles are said to be bosons, there the particles are said to be fermions, depending upon their first name, right? So bosons do not follow Pauli's exclusive principle, therefore any number of boson would be in one quantum state, ho sakta hai. What is the condensation phenomena? Condensation phenomena is that if I decrease the temperature of the system, then the particles associated in the excited state would be rushed, accumulate towards the lowest energy state or the ground energy state, because there is quite possibility for those number of bosons in one state possible hai. Whereas on the other side, if I take the system of fermions and if I lower down the system temperature, then the fermions also accumulate toward the lower state experimentally, but it is looking as a violation the rule of Pauli's exclusive principle. No two particles in one quantum state. How condensation phenomena is possible for fermions, right? सबके सब fermions एक ground state में जाएंगे तो अपन बोलेंगे fermi condensate. Otherwise नहीं. तो उसकी डेंसिटी उतनी बढ़ना चाहिए. As you know, in case of the semiconductor, every energy level has been completely filled by each electron, right? वो follow करता है. Electrons are fermion. But condensation when I talk about, specifically, there was experiment who could show the Fermi condensation. It is against the Pauli's exclusive principle. ये क्यों ऐसा हुआ है? So this indicates that the occupation number is 0, 1. एक तो वो स्टेट एम्प्टी रहेगी 0 या फिर फील्ड होगा 1 से ही, दो कभी नहीं आएंगे, बिकॉज ऑफ फॉलोइंग Pauli's exclusive principle. No two would be in one quantum state. No two or more than two, I mean, best. इसलिए दो नहीं दे सकते अपन, right? This is the equation with which you can easily calculate the mean occupation number. Mean value कितनी होना चाहिए? That particular mean occupation number calculated as the function, that is bosonic function and fermionic function. Okay. What are the bosons and what are the fermions then? All integer spin particles, all half integer spin particles, right? This is the difference between the two. And neutral atoms with an even number of neutrons are bosons. कोई ऐसा एटम होगा न्यूट्रल एटम जिसके अंदर में न्यूट्रॉन की संख्या कितनी है? So if it is even, all are boson. If it is odd, all are fermions. These are quite differences between the two. If you look to the helium isotopes, helium-4 and helium-3. Helium-4 are boson, helium-3 are fermion. Why? You can find the differences. Number of neutrons is 1, number of neutron is 2. That is the main difference. And accordingly, you can find the He4 boson and He3 fermion. He4 also show the condensation, He3 also show the condensation. Now question again keeps in our mind that how it is possible for He3 to show condensation. Means He3 particles in one quantum state for fermions. It is beyond our digest, right? But it is experimentally verified. That we are going to look to this particular matter. Standard particle model for bosons and fermions, it is very simple. Leptons and quarks all are 6 types of leptons, 6 types of quarks are fermions, and these are the bosons. Okay, that we can have the identification which bosons and which are fermions. We can take for understanding the condensation phenomena for them. Now, symmetry of wave function is very important to understand the Fermi condensation process, whether it is possible or not. Okay, and the number of particles in the one quantum state is applicable for bosons, and number of particles in one quantum state is not applicable for fermions, can also be clearly seen from this. When I look to this particular left side diagram, it indicates that simply for better understanding through quantum mechanically approach as these are the quantum states. One quantum state contains a particle whose name is A and the state is nth. So in nth state the particle is A. Quantum mechanically it is identified as psi and A. Its energy is E and A. Similarly for that case, psi Kb and E Kb. Right? Now if, so it is very simple. One particle in one state. Right? Now if there are two particles in the two states, A in n and B in k, how can I express their wave function as a product? Why it is product? And energy is added. So it is wave function dealing with the probability, and therefore it satisfies the multiplicative rule and energy satisfies the additive rule, and therefore it is a product of that. Means this product psi and A, psi Kb would be the wave function associated for the system having A in nth state and B is in kth state. But is it really the wave function applicable which I have mentioned? No, it's not the correct. That we want to check it. Right? If I interchange AB, A would be in k and B in n. Its wave function is different. So as a symmetric wave function, earlier we have seen that if I interchange the particle, there would not be change in the wave function in sign. For fermions, there would be change in its sign, keeping in mind this difference. And therefore, most general way of expressing their wave functions for occupying number of particles in the different quantum states, how can we express in general as a linear combination of these two? So if I add it together, that wave function is said to be symmetric. and the linear combination with minus, that would be considering as antisymmetric wave function as a determinant that we can express, that we can see in the different books even. So if I interchange, you can find no change in the wave function as a symmetric, and if I interchange, there will be find the interchange, that we will find the change in the sign for the fermions. Okay, so here it indicate little beyond A1 in N1, A2 in N2, A3 in N2, and so on. If the numbers are filling individually in the different states, you have that summation. अभी हमने देखा ना, this plus this symmetric, this minus is represented by determinant. मतलब हम ज़्यादा particles को apply करने वाले हैं. So symmetric wave function in that case and antisymmetric wave function in that case. It's very obvious. Now, interesting is this. If you have a system like that, all such kind of the particles are in one quantum state. एक quantum state में अगर ये particles होंगे, so it is applicable for symmetric but not applicable for antisymmetric, that we can check. So if this is the situation, its wave function would be like this. देखो आप देख सकते हैं N1 में ही है पूरे N1, right? Their names is A1, A2, A3, A4 and so on. That would be the wave function for this situation. इसमें sum करने की जरूरत नहीं. Why? Because I'm talking about only one state as that energy level N1. But what about the determinant? Here in this case, if I interchange A1, A2, बदल भी दिया तो इसमें कोई फर्क नहीं पड़ने वाला. So wave function retains as it is for symmetric, for bosons. No change at all. But this is the wave function in the form of determinant for such situation, for antisymmetric. If I interchange, two column get interchanged, then we get the 0. Means the wave function vanishes. Now vanishing of the wave function represent that this state is not allowed for fermions. So this is the symmetry of the wave function with which we can understand that any number of boson can be in any quantum state, specifically for boson, but for fermion, no two or more than two fermions in one quantum state. अगर यहाँ दो भी रहते या फिर दो से ज़्यादा होते तो determinant 0 होता. So that do not allow for substituting or putting all those numbers in the one quantum state. So this tells us this particular idea. This is the logic behind it, and therefore again I am coming to this particular. If you have thought what would be the nature for this particular case, anybody? While looking to these basics of that quantum statistics, what would be the nature? हम वो कुछ सोच सकते कि मतलब पॉलीजेस्टिक प्रिंसिपल के हिसाब से सोचना है. ये तो obvious है. Now this is the pen, two pen I have. I can offer both to one. मतलब एक quantum state में दो हो सकते हैं ना, वहां नहीं हो सकते, वो कट गया. ठीक है. Here in this case, ये भी possible है, ये भी possible है. यहाँ पर PB और BP interchange हो गया, right? Because we can identify what is book, what is pen. Here both the pens are same. मतलब मैंने A X को दिया, Y को दिया, interchange किया तो मुझे तो same ही pen दिख रहे हैं. Therefore I have only one state, right? This is the state. Similarly for X, Y, Z, similarly for X and Z. I can look to this. But for that case, वो O जो है वो भी similar है to O. What would be the nature of the O? P मतलब मैं एक P पकड़ लिया पेन. अब पेन कैसा है कि हम देख सकते हैं उसको. But when we talk about the boson, we are not able to see it again. That we have to apply in this particular case. So what would be the nature then? How can we apply this logically? मतलब दो ऐसे कोई है जो मैं एक को नहीं दे सकता, यहां दे सकता हूं, right? Both gift I can offer to one, either X or Y or Z. Right? ये तीनों वहां पर आ गए, but ये कट हो गया. Means I cannot offer both to one. कट हो गया because of Pauli-Exclusion principle follows by that type of gift, that is fermionic gift. ऐसा क्या हो सकता है कि हम नहीं दे सकते? अभी आपको दिखेगा. Can you see? Very faint. Can you see? The example would be like that. This is one of the examples. You can have different kind of the examples. Vacancy. If I have a team of football, 11 players लगेंगे मुझे, right? I need 2 players. मतलब वैकेंसी मेरे पास कितने हैं? तो मैं दोनों के दोनों एक टीम में अगर रखूंगा ऐसा तो नहीं पॉसिबल होगा. सो आई हैव टू ऑफर इंडिविजुअली. एक्स को देना पड़ेगा, मतलब एक्स और वाई को सिलेक्ट करना पड़ेगा, या फिर वाई और जेड को करना पड़ेगा, फिर एक्स और जेड को करना पड़ेगा. मतलब दोनों का दोनों वैकेंसी में एक को नहीं दे सकता हूं ना. इफ आई ऑफर बोथ द वैकेंसी एज अ गिफ्ट टू वन, इट इज नॉट फुलफिल्ड माय 11 टीम. मुझे 10th मिल जाएगा, राइट? So to fulfill that, I have to offer individual. So individual would be the vacancy. This is one of the example, best suited example to understand Pauli's exclusive principle is applicable for the case like the gift as vacancy. So that would be best suitable example to understand clearly for fermion. मतलब ये दो हो ही नहीं सकता, right? And therefore the question comes the same thing, that how can large number of fermions would be in ground state during condensation process. That process is said to be fermionic condensate. ये question अभी भी हमारे पास है. To solve that, I am coming to this particular case. Now I am talking about the contribution of Bose, Satyendranath Bose. Here his paper is written there in 1924. It was very interesting that he was working as associate professor in Dhaka University. Mention it there. Dhaka University. Earlier it was in India, now it is in Bangladesh at that time. So he was Indian philosopher. He written the paper with title Planck's Law and Hypothesis of Light Quanta, specifically related with photons, because I am coming to frozen light. He was the person who thought on the photons. Why? Because you know that Planck's Law in 1901, who is the main of quantum mechanics? Planck's. Who has derived Planck's law? Different Wien's law, Rayleigh-Jean's law, Stephen's law, all those laws from thermodynamic point of view and applied for quantum. But the person, Satyendranath Bose, through this paper expresses that all such laws of radiation can be easily solved with the help of quantum statistics known to be Bose-Einstein statistics. Later on, the name has been given for such a theory. But when he has wrote the paper and with this title sent to the journal Philosophical Magazine, at that time the paper was rejected. Because we know that we are the researcher, we generally send some paper to the journal. Most of the times journal reject that paper because if the editor do not find something new. Likewise. So he was very much disappointed, and therefore he thought that Einstein was very famous on those days for the photoelectric effect. He just wrote a letter and sent this paper as it is to him. That is, when you see his biography, you can just find. Einstein read it carefully, and who could understand the meaning of the Bose idea. So he just same paper converted into German language and published in German magazine, that is Gestrip for Physik. That was German language journal. So it Z Physics 26 pp 178 181 in 1924. That paper was published in German journal, and therefore Bose's name was popular because his name was associated with Einstein. So earlier his paper name was only Bose, then later the Bose and Einstein. When it was published in German magazine, Bose and Einstein, and the Bose become very famous in that. And with this paper, then Bose-Einstein statistics that we are studying today, which is given by Bose itself, because Bose was the origin. Einstein was simply follower to his theory, because whose name was very popular on those days, and therefore with his name the paper could published, and therefore Bose-Einstein statistics was coming out, and therefore we can see now Bose-Einstein condensation, the fifth state of matter, our Indian philosopher before 100 years has given. Before 100 years, 1924. Today we have 2024, 2025, 2026. I am talking about frozen light after 100 years. Theory given by Bose, but experiment related to frozen light, which is definitely useful for developing today's quantum computer. Italian scientist experimented, show the meaning of how this is possible of Bose's idea that condensation of photons. So photons considering as condensation was not possible on those days for photons, but today it is possible because photons is not directly condensate. Photons gets converted into polaritons. It is a dressed material of the photons that we see what does it mean. So this is exactly a fifth state of matter theoretically given by Bose. But Bose could not get the Nobel Prize for giving the theory only. But experiment was those who have done related with these who could get the Nobel Prize in 2001. This kind of the theory he has given in 1924. So you may have a question that from 1924 to 2001, it has taken around 75 years for this type of the theoretical idea given by Bose and experiment done because of very low temperature around 0 degree Kelvin was not possible on those days. Right? So before getting the fifth state of matter experimentally to Eric Carnell, who was awarded as a Nobel Prize in 2001, before that, the discovery of the refrigerator with the help of the magnetic effect, with the help of the laser cooling, and then it was possible to show the condensation because the system can undergo to 0 degree Kelvin even. Therefore, not possibility, and therefore it has taken that much of years. So what is this condensation then? It is very simple that if the number of particles are moving toward the lowest energy state as the temperature of the system is decreasing. So there is a certain critical temperature below which all the particles are now accumulating toward the ground state, and it is quite possible for boson, and therefore theory is given by Bose and experiment for different kind of the materials as atomic gases, some halide type of the gases that can also be possible even today. Okay. So this is the theory given by Bose. I am not giving you much more detail related with that because within 1 hour, how can I explain everything, right? So you have to go through this if you want that particular idea. So then Einstein formulated some formula for TC. TC is the critical temperature to be designed for a particular gas, which is depending on the rho. Rho is the density. So density of the gas, and similarly, of course, you can consider that what would be the particular temperature required to condensate for a gas, and from this particular point of temperature, it is easy for experimental to show that. So this particular diagram tells us that when there is a temperature Tc, critical temperature at which the number of particles in the ground state, NO stands for number of particles in the ground state, the energy is 0, and the number of particles in excited state, Ne, right? It is equal to N. Above the critical temperature means at room temperature even, which means that all number of bosons would be in excited state. अभी ये room temperature में है हम लोग, तो boson के बारे में जब हम बात करेंगे, photons, if it is an example, then all would be in excited state. If the temperature is decreased, come to critical temperature, then again coming toward the 0 degree Kelvin, then it comes to the point that Ne would be 0, means there would not be any particle in excited state. कोई excited में नहीं रहेगा. All would be in the ground state, that is NO becomes N. Total number of boson would be the same. ये कोई सिस्टम में जितने होंगे उतने सेम रहेंगे, कुछ ऊपर रहेंगे कुछ नीचे रहेंगे. जैसे हमारे कूलिंग सिस्टम चालू हो गई तो ऊपर से नीचे आना चालू हो गई, right? This is the way of understanding of condensation process. The theory has given by Bose. Then some kind of the superfluidity come out later on in 1938. showing for Bose-Einstein condensation. But it was not applicable as the case of as direct adequate applied by the Bose. So many theories related with that of superfluidity to understand. So why I am taking this particular superfluidity? Because frozen light as one of the state of the matter that has both characteristics. One is supersolid and second one superfluid. Therefore, there is a necessity to understand the meaning of superfluid. So superfluid liquid helium He4 as well as He3 both can show. Earlier we have seen He3 is fermion, He4 is boson. So I am talking about Bose-Einstein condensation. Therefore, the example is He4 as a boson. So if I take a system of He4 and cool down, then it also shows such kind of this Bose-Einstein condensation. Only the differences in experiment as per the theory given by Bose, some differences to be noted. Why this happens? Because Bose has given theory considering its ideal condition, which means that bosons are not interacting at all inside the system. But this is not practically to be applied. If you take the example of He3 or He4, those particles have weak interaction, not a strong one. Weak interaction that cannot be avoided. And due to such weak interaction, there is a possibility of not or mismatching between theory and experiment. That was the case, and different models have been proposed. Tisza model, the London model, Landau model, as well as the Feynman model. All those models have been applied for superfluidity. The meaning is that superfluid is one nature of the matter which has zero viscosity, which means that it is a frictionless motion. Viscosity is zero hai, so nobody is able to catch it. It has no resistance at all, right? So such kind of the material is also possible, theoretically given by Bose, but practically experimentally shown by different. So these are the different theories have been given, Landau theory and the Feynman theory, in respect of what is specifically for that particular case. If I look to this diagram, left side type, so it is also a particular critical temperature, specifically lambda, the name is given that its value of increasing specific heat versus temperature as curve like a lambda, and therefore it has given the name lambda. Critical temperature is T lambda. So above T lambda, the liquid helium is He1 and the liquid helium He2. So this particular helium is always remain in the liquid state even at 0 degree Kelvin. Always. Because its 0 point energy is very large and they have the weak interaction of the particle itself inside. So this superfluid, so normal fluid below, above the critical temperature and below the critical temperature, that is superfluid. So this particular superfluid consisting according to Landau, that it consisting of the excitation, and there are the two types of excitation. One is said to be phonon, second one is to be proton, and their energy is depending on their momentum. And therefore, these are the two expressions depending on the momentum energy for specifically for phonon and protons. So which means that superfluidity can also be occur and theoretically explained with the different models. Superfluidity of liquid helium can be thought about like this. When we can fill in a particular jar, it will not remain as it is. आप अभी वो सुपर फ्लूइड अगर आपको किसी ने दे दिया, देख लो भर के खाली हो गया. So it seems that like, okay. So nobody is able to catch it because its viscosity is zero. आप water भी लेंगे, water has viscosity, right? वो रहता है, but that superfluid is not possible to hold it. So it can move. ऐसा भी होगा तो बाहर निकल के ऐसा करेगा या फिर अंदर निकल के ऐसा करेगा, which means that there is no catching of such liquid in a particular container. There were so many experiments on Bose-Einstein condensation. So here 1938 Kapitza for He3 and there He4 and 8% was showing condensation as adopted by the theory given by Bose. Only 8% because of weak interaction, not 100%. So first pure BEC was shown for rubidium 87 atoms, those are bosons, and which obtain at 170 nano Kelvin, and therefore Eric Carnell and his team could get the Nobel Prize. So these are the different experiments you can find. And at the last, I am coming to this particular recently, because I want to go in a very short period for the frozen light in 2025, last year. Italian scientists showed BEC, Bose-Einstein condensation of exciton polariton. This is new, of course, exciton polariton as photonic supersolid. I am talking about this particular, because there are so many experiments covering up for the different kind of these atoms for Bose-Einstein condensation. Now again the question comes in your mind that what about the fermionic condensation, right? It is related with bosons. Boson can show this particular idea, but fermion can't show at this very beginning because it follows the Pauli's principle, right? So these are the three persons who could get the Nobel Prize in 2001 for showing experimentally first Bose-Einstein condensation. Okay. Now I am talking about this fermionic condensation. What is the theory behind it? Ideal Fermi system at the beginning, which tells us that how the electrons are filled in the different states. It is very obvious, everybody knows that every quantum state can contain a maximum of 1 electron. Below the Fermi energy level, all are completely filled, each by 1 in every quantum state. Then above the Fermi energy level, all are completely empty. This is the situation, right? Now, if this situation, this system, if I take for condensation phenomena, then how it is possible for those electrons would be in ground state? मान के चलो यहाँ पर 100 इलेक्ट्रॉन होंगे, 100 इलेक्ट्रॉन ग्राउंड स्टेट पे आ गया. That process is said to be condensation. Is it possible for electrons? No. Why? Because electrons follow Pauli's exclusive rule, and therefore only one in one quantum state, not all. But it was possible to show. ये तो डिफरेंस है. चलो जल्दी भागते. टाइम कितना है दोस्त? मुझे थोड़ा उस पे फ्रोजन लाइट पे आएंगे, थोड़ा ये अभी बेसिक्स है. So that is, you can have the idea, understand fermionic condensation. The first atomic potassium. अब मैं यहाँ पर आ रहा हूँ. That is the difference. I hope that you have understood what I want to express, right? First atomic potassium K40, which are fermions, condensate was created by Deborah Jean in 2003. 2001 में जब ये नोबेल प्राइज मिला Bose-Einstein condensate को, so many scientists thought about why not for fermions. They tried to show for fermions even without considering Pauli's exclusive principle. 40, potassium 40 as a fermion, they could take as a system and cool down the system. And experimentally, they could get it condensate. It is against Pauli's exclusive principle, right? But Deborah Jean was unable to explain the theory behind getting success of experiment of fermionic condensate. It was quite unable to explain. Experiment हो गया, okay? Fermionic condensate. The lady is Deborah Jean, I mean, in 2003 in MIT. You know MIT, where they could show that kind of the fermionic condensate. What kind of the fermions they have chosen? Potassium atoms. Potassium 40 is one of the isotope of potassiums, which are fermions. And they have experimentally shown Fermi condensate. अभी हमारे पास question आता है, how it was possible? So many models to be applied. But at that time, when I was in Shivaji Science College, Sir Dharmadikar sir was also at that time, and he was just retired in 2003. And we have joined in 2003, and there was a flash news of 6 state of matter exist. आपको याद है सर? 6 state of matter. But it was not a 6 state. तो उन्होंने बताया कि this is a new state, because Bose-Einstein condensate is the 5th state, Fermi condensate is the 6th state. तो उन्होंने fermion को लेके किया हुआ है. But it has not been accepted. Why? Because there must need of theory behind it. Because it is against the Pauli's exclusive principle. What was the theory? What was the Pauli's exclusive principle to be applied? How? So, debate was there. Then, fermionic superfluidity as a superconductor. You know superconductor. Superconductor is the Fermi condensate exactly for electrons. Exactly it is. मतलब इलेक्ट्रॉन ऐसे क्या जा सकते हैं? पूरे के पूरे इलेक्ट्रॉन से जा सकते हैं, विच मीन्स दैट कूपर, बार्डिन एंड शिपर, बीसीएस थ्योरी बोलते हैं, हम लोग सॉलिड स्टेट फिजिक्स में पढ़ते हैं. बीसीएस थ्योरी come upon for understanding of fermionic condensation showed for potassium 40 by Deborah in 2003, and BCS theory tells that it is possible experimentally, but it is not a new state, it is the same state that of the bosonic condensation. जो बोसॉन दिखाता है वो ऐसा ही है, but it has initially chosen for fermions. fermions को लेके अगर हम बोस के बारे में बताएंगे तो फायदा क्या? So which means that they have chosen initially the fermion, and the condensate is said to be fermion condensate, not a bosonic condensate. But BCS theory tells that because of when such kind of the fermionic particles cool down to near to 0 degree Kelvin, they will change their spin at 0 degree Kelvin. One electron, second electron will change their spin by forming their pair, right? And that pair is said to be Cooper pair. In the superconductor, BCS theory has well explained Cooper pair. So Cooper pair of electrons. So when all those electrons at 0 degree Kelvin come to ground level, it is possible now by forming pair, electron-electron pair, electron-electron pair. So half integer spin of electron, half integer spin of electron become one integer, right? One integer is the spin of boson. मतलब कूपर पेयर बन गया बोसॉन, इलेक्ट्रॉन है फर्मियन. दे स्टार्टेड विथ इलेक्ट्रॉन, पोटेशियम 40, इलेक्ट्रॉन के बारे में नहीं, ये सुपर कंडक्टर इलेक्ट्रॉन के बारे में. सो पोटेशियम 40, these two atoms having the spin half joined together forming pair becomes a composite one, and composite is nothing but a boson. And when they become composite, they become boson. What is the new state then? It has started from fermionic, it has converted fermionic to boson. So it is nothing but boson condensation. Therefore, it's not a new state. Experimentally, it is fermionic condensate because fermion show this. But theory says that it's not a new state because it is simply composition form, and therefore it is possible. So superconductivity, Cooper pair for electrons, ये theory वहाँ थी. Then superfluid He3 एटम्स पेयर, फिर इसके He3 पे भी चालू हो गया बिकॉज पोटेशियम 40 ने दिया तो He3 भी देगा. तो सो मेनी fermionic condensation was started experimentally, but it's not a new state. Therefore, today even we don't have any sixth state of matter. Though you just search through Google, it is expressed as the sixth state of matter is the fermionic condensate or Fermi condensate, but it is not, because we know the theory how it is possible. So it is not possible theoretically to be applied for such Fermi condensation, though experiment shows, but they will change their identity, fermion convert into boson. That was the point, and therefore the question mark earlier we had. But one or two questions again you can have, that how the electron will form a pair, negative charge, right? How it can be possible? Positive charge, negative charge can form a pair, but both are negative charge. They will be repelled from one another. That was the another question, and it has been completely overcome from this particular theoretical idea given by the BCS theory. So this is the particular lattice. This is related with BCS theory, specifically for electrons present in the atoms. So atom, they are arranged in the periodic arrangement and lattice. So whenever one electron is free from an atom, for let us consider that electron 1 and electron 2, how they form a pair. So they are not simply form a pair as a binding together between the two electrons, they are forming the pair through the lattice vibration, and lattice vibration is nothing but the generation of phonon. And therefore we can say that it is the virtual phonon who is the cause of keeping the pair of two electrons. दो इलेक्ट्रॉन को जोड़ के रखने वाला जो बीच में है, that is a phonon. So phonon is nothing but the quanta of sound, and it is due to the different mode of vibration of the lattice. So whenever one electron is formed, another electron is formed. So just we can understand that the lattice will vibrate. अगर क्लास में पूरे बॉयज बच्चे बैठे हैं, गर्ल स्टूडेंट कोई आ जाएंगे, सब बॉयज थोड़ा सा यहाँ अटेंटिव कम हो जाएगा, लेकिन थोड़ा मुड़ के देखना चालू हो जाएंगे. That is quite possible, right? This is the disturbance. So disturbance caused by the one electron, and therefore these two electrons will be trapped by the vibration of lattice, and those trapped electrons will form a pair. And this pair will move inside the lattice, and therefore it is quite possible to observe the superconductor. And superconductor and conductor, we can find the difference that below critical temperature, the superconductor offers zero resistance, whereas conductor, you can find even at 0 degree Kelvin, it has certain resistivity, right? So resistivity would be zero below critical temperature. That is superconductor. We can understand with this logic, we are able to understand the case of non-occurrence of the sixth state of matter, whereas it is existing for Fermi condensate. Now, as per my title related with this frozen light, because this was the necessary theory to use as Bose-Einstein condensation for applying to frozen light. Now, frozen light is nothing but photonic supersolid. I mean, now you have a question: super solid, superconductor, superfluid. Right? Those are the different words. So, photonic supersolid. So, supersolid is a specific quantum type of material having both characteristics of crystalline nature of solidity and frictionless characteristics of fluidity. How it is possible for that case, and therefore it is said to be unique state of matter. Okay, so this is quite possible. Before to understand experiment related with that of frozen light, how the light gets trapped, we must know about the meaning of exciton, we must know the meaning of polariton. Okay. So exciton is nothing but what? Whenever any semiconductor material is excited by the photon. Try to understand. Any semiconductor material is excited by the photon. What happens? A semiconductor material has a band gap, electron in the valence band, right? That electron will be excited by absorbing the energy from the photon. Now the energy of the photon must be greater than the band gap, then those electrons will be moved from valence to conduction band. Everybody knows that is the simple idea behind it, right? So this indicates that the energy of the photon is now absorbed by the electron in the valence band. That electron will move to the valence band, conduction band, leaving behind the hole, right? इलेक्ट्रॉन का नेगेटिव चार्ज चला गया तो पॉजिटिव चार्ज आ गया, ऊपर नेगेटिव चार्ज हो गया. सो व्हेनेवर इट गोज टू अप डाउन, व्हाट इज रिमेनिंग इज opposite charge of hole. So hole and electron form a pair. That pair is said to be exciton. So exciton is created. Exciton doesn't remain as it is in the semiconductor. It gets created as and when the electron present in the valence band gets excited, having more energy than that of the band gap, and therefore forming the exciton. That is nothing but the exciton. Exciton is a quasi particle, right? वो वहाँ पर रहता नहीं है. It creates. Okay. So this is the meaning of the exciton, that we can see that simply even in that particular case. And whenever the exciton is formed, how they move? So they are orbiting. Hole is orbiting around the electron, and electron is orbiting around the hole. That is clearly seen. That is the nature of moving of the exciton. So excitons are the bound states of photo-excited and Coulomb correlated electron-hole pairs produced by light illumination. Okay, right? Of energy greater than the band gap of the semiconducting material. There are two kinds of the excitons created in the semiconductor as and when they are electrons get excited by any other means. So one is said to be Motte-Wiener type of exciton. Second one is the Frankel exciton. So Frankel exciton is generally observed in nanostructure semiconductor material having lesser value of the dielectric constant. Whenever the dielectric constant of a particular semiconductor material is large enough, then the Motte-Wiener type of exciton will be created. Such exciton pair electron hole, the distance between such a exciton is very large compared to their atomic spacing. But there it is very small compared to the atomic spacing. Therefore, we need to have the nanostructure semiconductor for observing the exciton of very strong attraction between the electron and hole. इलेक्ट्रॉन एंड होल का जो अट्रैक्शन जितना ज्यादा होगा उतना लाइट फ्रोजन करने के लिए पॉसिबल होगा. सो विच मीन दैट वी हैव द नीड ऑफ nanostructure semiconductor material. So what was the idea of the Italian scientists behind it? Italian scientists have successfully demonstrated that light can behave like a supersolid. Now this is the question. Light as supersolid. How light can get change its state, right? That light can behave like a supersolid, a state of matter that exhibits both a rigid solid-like structure and the frictionless movement of the fluid. So whenever the light gets trapped in a certain material, then that material is having two properties like super solid as well as super fluid. सुपर सॉलिड मतलब क्रिस्टलाइन नेचर और जैसे कि वैसे ही है, पहले से क्रिस्टलाइन नेचर है, एज इट इज रिटेन, बट इट गेट्स सुपर फ्लूडिटी एंड देयरफॉर दिस इज वेरी important to understand that superfluidity nature of that super solid material as and when the light gets trapped, requirement of fast movement of our digital information, and therefore it is helpful for development of quantum computer. This is the base compared to that of superconductor. सुपरकंडक्टर में इलेक्ट्रॉन की मोशन जो होती है उससे ज्यादा फोटोन की मोशन होती है, बिकॉज वी नो दैट द वेलोसिटी ऑफ लाइट is greater than the velocity of even electron. There is nothing object moving faster than that of the light. And therefore, whenever we use light as a photon, and therefore photonic super solid, if you are able to form, that would be the best option for fast transmission of data, and it is the today's need of developing of quantum computer. Okay. The team achieved this by creating polaritons. Now our aim is to understand polaritons. Exciton we have seen clearly. Polaritons. Hybrid particles of light and matter. So it is half light, half matter. This groundbreaking discovery opens new avenues for understanding and manipulating light and matter at the quantum level. So quantum mechanics to be applied. So this is very quite interesting. That is the need of today's understanding. New technologies in quantum information processing. So that would be help. It is according to this Italian. How the Italian scientists achieved? So creating polaritons, laser interaction, supersolid formation. The experiment simply tells us that whenever light is irradiated for a semiconductor material, that is of nanostructure, and it is what kind of the semiconductor they have used? It is gallium arsenide of 2D type. 2D type means two-dimensional, which is quantum well, nanostructure one, and which is filled between the two reflector, strong reflector. You can see the right side diagram. That was the experimental arrangement given by Italian scientist, and second one indicates related with such kind of this phenomena in the Italian lab, and they have published in Nature. So you can see the March 2025, their published work related with this emerging supersolidity in photonic crystal polariton condensates. So which means that what kind of condensation it is? Bose-Einstein condensation. So polaritons, whenever they are not exist inside the material like exciton. Exciton creates, likewise polaritons create. So polaritons are again the quasi-particle. It has half part of light and half part of matter. Therefore it is called quasi-particle. So it's a quasi-particle. वो light के वजह से बना हुआ है and matter के साथ interact होने के बाद. So whenever light gets interact with the matter, what should be the matter? Matter should be of nanostructure, that kind, because it requires some microcavity ridges in which the polariton needs to be developed. Okay. So method is very simple. The material is fired by using the laser, and when we consider the laser as a light, and these are considering as a photon. Quanta of light is nothing but the photon that we can have. So whenever the light gets trapped inside the material because of multiple reflection between the two reflectors, तो light को बाहर निकलने की जगह ही नहीं है. So it gets trapped and light is accommodated in the all micro cavity regions of the semiconductor. So what happens inside? Whenever the light irradiated with the semiconductor, which is responsible for the creation of exciton. Electron in the valence band goes to the conduction band, creation of exciton. Again, the photon is interacting with exciton, forming photon, exciton forming polariton. So polariton continuously forming and occupying the micro ridges, micro size of the cavities present in the semiconductor that is known as nanostructure, and those polaritons will be now increasing in the density depending upon the density of the photons, and all such photons gets trapped forming polaritons, and therefore these are specifically known as exciton polariton. Why it is called exciton polariton? Because exciton is created by the photon. In metals, instead of creating exciton, plasmon gets created, and therefore there the formation of plasmon polariton. Okay, so there are the different kind of the polariton. Plasmon polariton in metals, exciton polariton in semiconductor. So this is the case of semiconductor, therefore exciton polariton. Therefore, polariton is the word boson considered, and therefore polariton get condensed. Now polariton is what? Polariton is created due to light. So whenever the photon comes, interact with the exciton, creating polariton, means polariton is the dressed material or dressed particle of light. Light के वजह से ही है. बच्चा पैदा हुआ तो माँ बाप की देन. Characteristics of all coming in a particular child. Likewise, that is the polariton is a child of the photon. It's a dress of photon, and therefore condensation of polariton is nothing but the condensation of photons. Right? So that photon get trapped, and therefore formation of polariton, and therefore condensation of polariton nothing but a supersolid. Supersolid has both property, and this experiment has been validated by theoretical aspect given by that Italian physicist. So direct mapping of the polariton density. So density of the polariton gets increased inside. So what was the concept behind it exactly? So the scientists know well condensation of photons in the form of polaritons is quite possible whenever such a system is under ultra cold temperature, right? Near about 0 degree Kelvin, it is possible for condensation, otherwise not. But that scientist has great advantage. He could show that instead of keeping the system at low degree temperature, degree Kelvin, only falling light on that material, then it was possible of not depending on temperature, whereas depending on density. Density and temperature, these are the two parameters with which condensation can alters. So at room temperature E1, that was the great discovery shown by him. At room temperature E1, condensation of polaritons means it's a dress of photon, quite possible, and that would be really changing the new world of quantum computing. Because today's quantum computing, which is in the developing stage, needs to operate at 0 degree Kelvin, you know. बराबर है सर. आज का क्वांटम कंप्यूटिंग जो भी यूज कर रहा होगा, it is at ultra cold temperature to be operated, not at room temperature. But this kind of the theory and the experiment is quite interesting to observe the quantum computing at room temperature even. Okay, so this is the theory behind it. What was the idea? And we are not interested for his theory which is given by him. Our aim is to understand what has happened, right? So theory is validated for the creation of polariton and the creation of supersolid. Supersolid is the combination of the solid nature as it is of the semiconductor and the frictionless fluidity. That frictionless fluidity is important for useful of transmission of the data, and therefore quantum technologies definitely benefited from this discovery as frozen light. So this is why it is called unique. Unique is nothing but both solid as well as fluid. Okay. Solid means the polaritons are arranged periodically, and fluid means those polaritons can move as a solid without any friction, and therefore whenever the light passing through such material, it has a very fast to transmit the data in the form of qubits. अभी हम qubits की तरफ चलेंगे, right? So this is the idea. Significance of photonic supersolid. This is the first time of supersolid has been created using light, which could lead to new ways of manipulating photonic materials and quantum systems. Unlike previous experiments, when I was talking about a very low temperature, ultra cold atoms, the light based supersolid might be more stable and controllable, making it an ideal platform for future computing and optical technologies. Quantum computing could benefit significantly from this discovery, as supersolid based photonic systems may provide a more stable foundation for qubits. Because binary digits we know for classical, but qubits to be formed for quantum. And this gives the qubit formation. So key advantage of quantum computing is that stable qubit networks, the crystal-like solid and organized structure of photonic supersolid allows for the organized arrangement of photonic qubits. This is the crystalline nature is responsible for photonic qubits and frictionless information for transfer. Because of the material behave as a superfluid, information can move without viscosity. मतलब उसमें से कोई losses नहीं होंगे, transmission loss, I mean. The data to be transmitted without any loss, because when we talk about the photons, photon never interact to each other. एक लाइट इधर से एक लाइट इधर कभी interact नहीं करेंगे. Those photons cannot also be or less interacting with its environment. Therefore, we don't require much more shielding specifically for transmitting data. On the other hand, today's quantum computer, with the help of superconductor, with the help of motion of the electron, needs proper shielding of transmission data, and it is to be operated at 0 degree Kelvin, because it is superconductor, and superconductor is one of the characteristics of fermionic condensate to be observed at 0 degree Kelvin. Oh, 0 degree Kelvin में superconductor होता है. So scientists are applying to observe superconducting at high critical temperature, that is high TC, superconductor at high TC. So that is another discovery. But उसके पहले अगर हमको ऐसा material मिल जाए, which is now definitely useful compared to the supercomputer as superconductor as superfluid. So superfluid is nothing but the frozen light. अगर हम कर सकते, that would be the definite for today's an advancement of quantum computing, right? So photonic qubits for quantum computing, that is our part of its importance for quantum computing. So the difference between bits and qubits, 0 or 1, and we are understanding qubit as quantum state like a sphere. It is possible for 0, it is possible for 1, or both 0 and 1, right? Why use photons? It is speed of light compared to the speed of electron, the weak interaction surrounding के साथ में, and it is observed at room temperature. That is very much important and interesting, that is to be operated at room temperature. Therefore, the new quantum computer compared to today's developed computer or developing computer would be operating at room temperature, and therefore fastest information carrier. Encoding information, that we can say that quantum mechanically 0 state and 1 state, horizontal as a 0 state and vertical as a 1 state, and therefore you can have the superposition of the two, the wave function associated with horizontal state plus plus the vertical state, alpha times horizontal state and beta times the vertical state as a combination, as a simultaneous occurrence of the 0 and 1, that we can have a superposition through quantum mechanically. And advantage and challenges of photonic qubits for quantum computing. So quantum entanglement is also possible for photonic crystals. That photonic crystal means photonic supersolid, I mean. How it is possible for quantum entanglement? Quantum entanglement is nothing but whenever we are talking about the number of photons in the form of polariton condensed, so there must be linkage between photon to photon. And quantum entanglement, you know that the Nobel Prize has been declared for that. So anybody on Earth and anybody on different in the galaxies, even planets, then there must be certain entanglement, right? So entanglement is quite possible for formation of this qubit in between the two photons, photon A and photon B. There is a correlation between such kind of two photons, and therefore quantum entanglement, which is the requirement of applying quantum mechanics for quantum computing, is also possible by using photonic type of supersolid. Means superposition as well as entanglement, which are the basic principle of quantum mechanics, require for quantum computing forming the qubit type of the bits. The key advantage means it is of course operated at room temperature, low noise because of less interaction with the environment, and it can be integrated And of course, the speed is very fast because of light is used. And current challenges, of course. While looking to this discovery, there must be some challenges to be overcome. Now, what is the loss, photon loss that we can have? The photon can easily get lost or absorbed in fibers and components, destroying the information even. This is quite possible for that. That can also be overcome. Then scalability, deterministic sources and interaction. Those are the little bit challenges for this new coming up photonic supersolid. Apart from all those challenges, the great advantage even forming as quantum internet. Through the photons speed, we are then able to interact with one quantum computer to another, thereby forming the network between the quantum computers is also possible. So this indicates that how we are able to form a particular materials to be useful to form the qubit. Binary digit we generally see in the electronics, we get 0, 1, state is off, state is on. That some kind of the electrons is required related with that. How it comes out? It comes out from a semiconductor material. It comes out from a particular transistor, PNP, NPN, field effect transistor, MOSFET. All are basic related with semiconductor through physics. कोई तो भी एक सेमीकंडक्टर ही होगा जिसके वजह से हमारे पास 0 and 1 के ऐसे दो बाइनरी डिजिट्स आए हुए हैं. Likewise, we require certain material to have a formation of qubits rather than binary digits. 0, 1 and 0 and 1. Different simultaneous states between these two states, quite possible to form the qubits, is now to be obtained from such kind of new discovery as photonic supersolid. So, आपको supersolid is existing. Supersolid is existing at a 0 degree Kelvin. Photonic supersolid means we don't require 0 degree Kelvin. One plus point. Another plus point is because of light is used, transmission data will be very fast, and therefore photonic supersolid has great advantage over the existing supercomputer and developing quantum computer, even of course over the classical computer, no doubt. So this indicates that this discovery of photonic supersolid as the frozen light, a unique or exotic state of matter, how it is important for developing the quantum computer. That was my point to understand you related with this through the statistical approach as Bose-Einstein condensation phenomena, because frozen light is nothing but photonic supersolid, and so photonic supersolid is nothing but Bose-Einstein condensation of photons or polaritons. And therefore, there is a need of understanding Bose-Einstein condensation to understand how do we able to create such kind of supersolid known to be photonic supersolid. That's all, right? Thank you for your kind attention, and if you have any questions related with that, I am able to answer anything. Sir, काय म्हणता? Not.
Why they do interact, though weak interaction.
Because actually in case of semiconductor, if you want to apply the FD, we have to take the metals instead of semiconductor, because in case of semiconductor, exciton gate creates. Excitons are nothing but the bosons. Therefore, bosonic theory is applied. In case of metal, if you take, then there is a name of the plasma, plasmon. Plasmon, that is the surface plasmon resonance, is the requirement for showing the blue shift in case of the nanomaterials of metallic type. So when I talk about the plasmon, in case of metal, there is only the electrons. Free electrons are there. So plasmon consists of nothing but the gas of electron. So when I apply the specifically this light, then electrons is there, plasmon is there. So creation plasma into polariton, that is known as plasmon polariton. So light is responsible for creating plasmon polariton, no doubt. But the polariton is created, it is nothing but the boson. And therefore, though it is applicable for electron, but the next state coming out as not a new state, it is again nothing but the Bose-Einstein condensation state, and therefore B states to be applied, not FD. वो डायरेक्ट आएगा उस पर, लेकिन अल्टीमेटली आपको बोस ही दिखेगा, बोस के बाहर जा नहीं सकते भी.
Can these frozen photons use for data transfer
Of course.
if it is so frictionless?
Of course, it is related with the data transmission, because data can be fastly transmitted through the movement of these or velocity of the light, rather than the velocity of the electron used in superconductor for supercomputer, for today's quantum computer even. So data transmission would be very fast because of light is used.
The advantage will be in the velocity. Photon travels with the tremendous velocity of light. When data is transferred, or data can be transferred, the data also will travel with the velocity of light.
You're right.
So that will be a great advantage.
So that is the great advantage of transmission the data in quantum. Therefore, quantum computer, when it is developed through such kind of the qubits form, so it has a great advantage of transmission without any loss, because of it has frictionless movement. जो frictionless movement कोई ऐसे इसमें नहीं है आज.
So one more question. When Cooper pair is formed, what is the spin index of Cooper pair? Cooper pair of electrons. I am talking.
Yes.
When Cooper pair is formed, it is as good as a neutral molecule or neutral atom. So what will be the spin of this Cooper pair?
Spin would be the integer spin. That's all. Half plus half. Electron has half integer spin. Electron has 1/2 h cross spin. Another electron 1/2 h cross spin. 1/2 plus 1/2 when they form a Cooper pair. So it becomes 1 h cross. 1 h cross is the integer spin. And integer spin related with the boson. Integer spin. Integer spin nothing but the boson then. म्हणून तो म्हणतो ना की इलेक्ट्रॉन जरी घेतले तर तो बोझॉनच बनतो. Ultimately, Bose has given a lot. We are not moving beyond the Bose. वो
Thank you.
फर्मी का कुछ रही नहीं है यहाँ पे.
Anyone else? Yugansh? Any question?
And therefore, we must think that Indian knowledge system is one of the subject for all students at undergraduate, I think. So Indian knowledge subject, there should be deliberately to introduce such kind of the Indian philosopher who has given a lot for today's development, again based on 100 years what they have given. So such Indian knowledge system should be taught for the students, for such Indian philosopher who has given lot, and foreigners now adopting the theory behind the Indian philosopher. Modern, right. तुम्हाला कसं वाटलं सर हा म्हणजे फोटोनिक सुपरसॉलिड हा नवीन फिनोमिना येत आहे? दिस इज नॉट एक्झिस्टेड, इट हॅज स्टार्टेड नाव. नाही ते तर आहे, ते तर म्हणजे 1975 लाच आहे ते, बिफोर 50 इयर्स. हां हां हां. So it has double advantage to be observed at room temperature and to be transmit the data very fast by using photons.
Excuse me, sir. Sir, at very fundamental level, if I like compare, if I combine this freezing light with relativity, then the relativity like effect of time dilation and freezing light can be combined together. So, is there any possibility that the effect of that is comparable to internal time and the external time field changes because of this?
I could understand what do you mean.
So if we are like merging relativity and frozen light together, then so the concept of time dilation is changed by the effect of freezing light itself, because so the entire speed of light effectively changes the time limits, and in time dilation, as we know, like faster we go, there is the change in that. So if you are freezing the light and so is there any in that particular frame of reference? सर इट्स जस्ट फ्रेम ऑफ रेफरेंस टाइम का सर. अगर टाइम जैसे कि लाइक लाइट एक पर्टिकुलर एनवायरनमेंट में फ्रीज करने का एक्सपेरिमेंट है विच इज हैपनिंग इन अ पर्टिकुलर क्लोज एनवायरनमेंट एट दैट पर्टिकुलर टाइम, then so there should be some difference between internal time and external time reference, right? So वो कैसे measure होगा if in this concept? That was the entire question. Okay, sir. Okay, sir. Okay, sir. Okay, sir. Thank you, sir.
So thank you so much, sir, for this insightful session. Now I request Professor Anwane, sir, to present a memento to our guest.
So, on behalf of Department of Physics and Indian Association of Physics Teachers, I appreciate the efforts of Professor Kondawar in preparing such versatile topic and coming all the way to our department to deliver it. As a token of appreciation, we are giving a memento and a diary to Professor Kondawar. I call upon Professor Kumbhare to propose vote of thanks.
Good afternoon. Good afternoon, one and all. I, Mr. Bhupendra Kumbhare, feel privileged to propose the vote of thanks on this occasion. First of all, I pay my humble homage to Dr. Dr. Punjabrao alias Bhusaheb Deshmukh and Rashtrasanta Tuklaji Maharaj. I express my sincere gratitude to Honorable Mr. Harshavardhanji Deshmukh, President Shri Shivaji Education Society, Amravati, for his motivation and blessing. I am highly thankful to our respected principals, Dr. O.S. Deshmukh sir, for his constant guidance and support. I extend my heartfelt thanks to today's speaker, Professor Subhash Kondawar sir, for his valuable and enlightening lecture on topic frozen light. I would like to thank Professor S.W. Anwane sir, Head Department of Physics, for his continuous encouragement. My sincere thanks go to Professor Dharmadhitari sir and Professor Tharabe sir for sparing their valuable, Thasare sir for sparing their valuable time. I would like to express my appreciation to my colleagues, Dr. Thangar madam, Dr. Shaheen madam, Dr. Pathre madam, Dr. Jadhav sir, Mr. Parakh sir, Ms. Kanchan madam, Ms. Devani madam, and Mr. Bhashish sir for their constant effort in making this lecture a success. I also thank our non-teaching staff, Mr. Roshan, Mr. Akshay, and Mr. Sudesh for their valuable support. A special thank to all students for their enthusiastic participation and commitment throughout the session. Last but not least, I thank everyone who has directly or indirectly contributed to the success of this event. Thank you one and all. With the permission of chair, I here declare that today's event has come to a close. I request all students to get certificate and fill this feedback form. For this, scan this QR code and you will get a certificate. Thank you, sir.